102. All right. Good afternoon, everyone. I'm Mark Lewis, the Executive Director of NDIA's Emerging Technologies Institute. And first, thank you to all the attendees for your support of NDIA and ETI, and thank you for joining us for today's webinar. Our topic is Rockets 101, which yours truly will be presenting. And it's a timely subject, considering we've just gotten the news of a rather dramatic launch failure from SpaceX, but rockets do tend to blow up from time to time. This webinar is part of our Tech 101 series, where we try to distill complex technologies down to introductory webinars with a focus on their national security impacts. We aim these webinars to the intelligent layman, so if you know nothing about rockets, this seminar is for you. If you know something about rockets, please hang on anyway, because maybe you'll learn something or get some new insights that you hadn't had before. Let me start with some administrative remarks before we get started. First, all attendee lines are going to be muted. So if you have a question during the webinar, please submit your question in the question box that'll be in the webinar panel that you'll see on the right-hand side of your screen. I will do my best to get through all the questions during question and answer, depending on how many questions we have, no guarantees. We are recording today's webinar. So that's for members who are unable to attend, or for anyone who's listened to the webinar and thought it was so wonderful you wanted to hear it again, or wanted to review some of the material that I covered. And within the next few days, we'll post that recording to ETI's YouTube channel. So, all right, so let me get started and talk about Rockets 101. All right, so let me start with a little bit of history. I think you all know that gunpowder was developed in Asia. We don't know exactly when it was invented. We don't know when rockets were invented. Some scholars suggest that it dates to as early as the 10th century. Others think it was the 13th century. We know the first rockets, what we would recognize as a rocket, were basically just powered arrows. So you'd shoot an arrow and have a little propulsive device on it to help its trajectory. Honestly, they weren't very effective. They weren't very accurate, and so the effectiveness was somewhat questionable. This technology migrated from Asia to Europe. Certainly by the 1400s, we see evidence of rockets being used, but they really came into their own as a weapon of war in the early 1800s. In 1808, Sir William Congreve, an engineer connected to the British Navy, developed what became known as Congreve rockets. And these rockets are memorialized in our national anthem and the rocket's red glare. So that was the British fleet shooting rockets at Fort McHenry in Baltimore as part of their assault on that fort. Why were rockets developed? Well, there were several attributes of rockets that the British thought were very attractive. One was they didn't have a recoil. When you shoot a cannonball out of a cannon, the thing recoils, and lots of logistics associated with that. You have to load a cannon from the front. At least at the time, you had to load a cannon from the front. So if you could launch a rocket from a ship, no recoil, and it was easier to launch. There was a downside to rockets, which is it's spewing at fire, which on a wooden ship with cloth and rope wasn't always a good thing. So there was fear of fire. And as Francis Scott Key captured, these rockets weren't very effective. They weren't very accurate. The British used them several times in the War of 1812. They used them in an assault on a town in Connecticut. They didn't really work very well. So it kind of fell into disfavor. We generally regard Robert Goddard as the father of modern rocketry. So he launched his first liquid-fueled rocket in 1926, obviously many, many centuries after this technology was first invented. But what was special about Robert Goddard was first he used liquids instead of a solid material to fuel his rocket. And then Robert Goddard developed a lot of the technology that's associated with rocket propulsion. He built very efficient, for the time, combustion chambers. He worked on the design of nozzles that are used to accelerate the gases at the back of the rocket engine. Even in later experiments, came up with guidance systems and ways of controlling the trajectory of his rockets with control vanes. Wernher von Braun obviously also played a key role in the development of rocket technology, and particularly military technology. He was the father of the V2 rocket. It was also a liquid-fueled rocket. Von Braun supposedly knew a lot of the work that Goddard had done and based his work on Goddard's work. The V2 is arguably the first modern era rocket-based weapon of war. I'll step back and tell you it was actually a relatively ineffective weapon as weapons go. Each V2 rocket cost about as much as a B-17 bomber cost the United States. They were single use, obviously, And on average, every V2 rocket killed about 2 to 3 people, which of course is terrible if you're one of those 2 or 3 people, but it was a terrible exchange rate. And I will say von Braun did some amazing things in the development of the V2 rocket. It really was a horrible weapon because it was really intended as a terror weapon more than anything else. But the design of the combustion chamber, the nozzle, control vanes, everything was really amazingly sophisticated. So that, I would argue, opened up the modern era. And of course, von Braun and his key leadership team made their way to the United States and were instrumental, although not the only people, but they're instrumental in further development of rocketry in the United States. All right, so with that background in mind, I think rockets are part of our everyday technology, and yet we still lionize rocket propulsion. If we want to describe something as difficult, we'd say it's not rocket science. And by the way, this is where I get to hold up my little nameplate that says rocket scientist. It's not really rocket science now; it's rocket engineering. And rocket science, rocket engineering is by today a very well-developed field, but still a field with lots of advances left made and lots of directions that we can take the technology. And I'll talk about those later. I want to start with some basic definitions. First, what is a rocket engine? You'll see various definitions of rocket engines, but I think of it as a propulsive device in which the fuel that enables that propulsion is entirely self-contained. So in other words, all the fuel that gets burned in a rocket engine is contained in a tank or several tanks or in some chamber associated with the rocket. And contrast that to, say, a jet engine, where the fuel isn't entirely self-contained. In the case of a jet engine, I have an inlet, a hole in the front of the engine, and I use oxygen that's in the air from the atmosphere to burn with jet fuel to produce my heat and thus produce combustion, right? Advantages of rockets: they can produce very, very high thrust levels compared to the weight of the engine itself. Rockets can also obviously work in a vacuum because they're not depending on having a hole in the front, an inlet, swallowing air with oxygen with which to burn the fuel. Disadvantages of a rocket: well, because rockets have to carry everything with them, they can lead to vehicles that are heavier than, say, their air-breathing counterparts. So as an example, imagine if you wanted to build a jetliner that was powered with rocket engines instead of jet engines. The range would be very, very small, because in addition to carrying the jet fuel on board the airplane, you would also have to carry all the oxygen. And that oxygen would displace cargo passengers. So that would be a really bad design. Now, the bottom line is, if you don't need a rocket, you want to use an air-breathing engine with an inlet. But if you do need a rocket, if you need lots of thrust for a given weight, or if you need to operate outside of an atmosphere, the rocket is clearly the way to go. All right, so that's definition number one. Another definition: thrust. What is thrust? And I think we all have an intuitive feel for that, but formally, it is the force produced by the engine that's acting on the vehicle in the frame of reference of the vehicle. And we're going to talk about that in a little bit more detail. But the thing to remember is Sir Isaac Newton told us that for every action, there is an equal and opposite reaction. That means if I spit momentum out one direction, I have to counter that with conserved momentum in the other direction. And that's what a rocket is doing. It's sending mass at a given velocity out the back, and that produces a reactive force that drives the vehicle in the other direction. Another term that we use to characterize the performance of a rocket engine is the specific impulse, usually abbreviated with the symbol ISP, sometimes abbreviated as I sub SP. Specific impulse is very simply the amount of thrust that I produce from a rocket engine divided by the rate at which fuel is expended to produce that thrust. Right, so let me say that again. It's thrust divided by the rate of fuel consumption. Think of it as bang for the buck. How much thrust do you get for amount of fuel that you're consuming? Now, when we calculate specific impulse, we could calculate it based on the mass of the fuel that we use, or we could calculate it based on the weight of the fuel. We do it based on weight, and that's just a units issue, because when you calculate it based on weight, the units of specific impulse come out in seconds. Right? If you did it based on mass, then the units would be different depending on which unit system you used, imperial units or metric. But everyone uses seconds. So we use weight of fuel and it all comes out in seconds. I want to distinguish specific impulse from efficiency. You will often hear people say that specific impulse is the efficiency of the rocket. That is actually absolutely wrong. Formally defined, efficiency is the amount of useful work, the useful energy I derive from my system, divided by the total energy that was available. And that's different from specific impulse. I could have a very efficient engine, that is, it uses all the energy that's available, that has low specific impulse. I could have an engine with a very high specific impulse that has relatively low efficiency. In other words, it's producing lots of thrust for the amount of fuel that it's using, but it's wasting energy in the process. So keep those two in your mind. And whenever you hear someone confuse specific impulse with efficiency, you can tell them I said that they were wrong, that those are two different concepts. Another important basic definition, delta V, change in velocity. That is ultimately what a rocket is doing. It's changing the velocity of a vehicle, and that change in velocity is delivered by a rocket engine. Now, why is that important? Well, on Earth, we tend to think of the performance of an engine in terms of the range that it can give me. You know, I've got a jet engine that will fly my vehicle a certain number of nautical miles, 100, 1,000, whatever. If I'm in space, once I start moving in a given direction without any perturbing forces, I will continue moving in that direction. So it's not meaningful to think in terms of range. Instead, we think in terms of the delta V, the velocity increase that I get from my rocket engine. And then finally, another important characterization for a rocket system is the mass ratio. That's the ratio of how much mass I have when I fill up all the tanks with all my fuel compared to how much mass I've got when I burned all my fuel. Think of that as a measure of how effectively I've designed the structure of my rocket, right? The lighter weight of the structure, the lighter the weight of the engine, the better my mass ratio will be. And as we'll see in a moment, that factors into the performance of a rocket engine. Okay, so keep those definitions in mind. We're about to do a little bit of math. My colleagues here at ETI said, don't put equations on the charts, but I'm going to put some equations. I'm going to respect your intelligence. We're going to walk through a couple of equations to talk about characterizing rocket performance. Okay, basic operating principles. And this is another thing I wanted to keep you in mind. There are actually two steps in the performance of a rocket. The first is adding energy to some working fluid, some mass that I'm expelling out the back. And the second is expelling that stuff out the back. So you add energy to mass, and that mass goes out the back. In chemical rockets, the source of that energy is also the source of the mass that goes out the back of the nozzle. Think about a rocket that, say, burns hydrogen with oxygen, right? Hydrogen plus oxygen produces water. It also releases heat. It's an exothermic reaction. The heat of a reaction is such that there's less energy in a molecule of water than there is in either the initial molecules of hydrogen or oxygen. The result is when I burn hydrogen and oxygen together, I get water and I get heat. That heat makes the water hot. And that kinetic energy is what is available to give me propulsive energy to do work in moving the vehicle. Now, in other types of rockets, I can actually separate out the source of the energy from the source of the mass going out the back. For example, instead of using chemical energy, I could have a nuclear rocket where a nuclear reactor is heating up some working fluid, maybe liquid hydrogen, and expelling that out the back. In that case, the source of the energy, the nuclear reactor, is different. It's coming from another source than the stuff that goes out the back of the engine. So that's another approach that I can take. So keep that in mind. It's a very convenient way to characterize the way rockets operate. Okay, now the equations that I promised you. Let's start off with deriving an equation for thrust. So force is equal to mass times the rate, is equal, I got a typo there. Force is equal to mass times acceleration, or really the rate of change of momentum. We'll correct that when it gets posted to the website. So that means that I can write the thrust of the rocket as equal to the rate at which momentum is moving out the back of my engine. That's equal to the rate of mass flow, which we give the symbol m dot. You see a dot over something that usually means something is changing with time, times the exit velocity, the velocity with which the stuff coming out the back of the rocket is moving. There's also a pressure term correction that accounts for differences between the pressure inside the engine and the ambient pressure. We won't dwell on that term because if we designed our rocket engine, it turns out that that's usually very small and we usually don't worry about it. Sometimes we bookkeep that pressure term in an effective exit velocity. Don't need to worry about it for the purposes of this fundamental discussion. All right. With that in mind, remember I said specific impulse is thrust divided by the rate at which fuel is consumed. So that's thrust divided by the mass flow rate times the gravitational constant. So that works out to exit velocity divided by g. We always use g on Earth's surface. It's a units conversion. So even if you're in space where there is no gravitational force, for example, you still do the units conversion of g. To rough order, g is 9.8 meters per second. If you want to do a back of the envelope calculation, g is roughly 10. So specific impulse tends to be about 1/10 the exit velocity. If I tell you I've got a rocket with a specific impulse of 450 seconds, you know the velocity of the stuff coming out of the nozzle is about 4,500 meters per second. Then finally, I want to show you the rocket equation. This is an equation that all rocket scientists, engineers memorize. It's the thing that drives our field. And that is the equation that tells you how much delta V you get, the velocity increment, compared to the performance of the engine and the weight for the mass fraction of the rocket. Delta V is minus G times specific impulse times the mass fraction. Now, why do I show you that equation? Because I want to point out there is a link between the velocity increase you get and the specific impulse and the mass ratio. And let's talk about that. As a general rule, higher specific impulse means more delta V, everything else being equal. So if I'm designing a rocket, I want to get the maximum specific impulse possible within some limits that I'll mention, right? That's why rocket engineers always strive to maximize specific impulse under certain constraints. Also, I want to have the most effective mass ratio possible. In other words, I want a mass ratio which is so good, the mass that's left over at the end of my rocket engine firing is as small as possible. That gets me the most velocity change. The ideal rocket is the rocket that basically expels all of its mass out the back for a given velocity change. Now, I'll also note thrust doesn't appear explicitly in the rocket equation. That's a little bit curious, but think about this. If I'm in deep space, for example, if I'm not in the presence of gravitational fields, for example, it doesn't matter how much thrust I'm producing. What matters is the effect that it has on the rocket, the delta V. Now, if I'm thrusting against gravity, for example, if I want to take off from the surface of the Earth, I need a thrust that is greater than the weight of the vehicle, or else I'm not going anywhere. I'm not getting off the surface of the planet. But if in deep space, thrust becomes much less important. The magnitude of thrust becomes less important. And I can have an engine where thrust, for example, is much less than the weight I would experience on Earth. I want to come back to the point that I made that you want higher ISP. Is higher ISP, higher specific impulse, always good? The answer is no. Under certain circumstances, I can come up with a solution where specific impulse is really high, but the mass ratio that results from that isn't very good. For example, in certain types of engines like electric propulsion systems, the mass of the engine dominates the mass of the system. And it turns out that you can show the specific impulse of an electric powered engine, which we'll talk about very briefly. Specific impulse is a function of the power that I can deliver to run that engine. Power scales with mass. So higher ISP can mean higher mass. So I get a yes on the ISP for an electric engine, but then I start worrying about the effect on the mass ratio. All right, let's talk about rocket nozzles. A rocket nozzle is an absolutely magical device that does this very simple thing. It takes thermal energy, heat energy, and converts it to kinetic energy. And how does it do it? Well, here I've got a schematic. It's a SpaceX Raptor engine, celebrate today's flight. And it's got a few major parts. One, there's a combustion chamber, right? Chemicals come in, they mix, they ignite, they produce products from that reaction. They also produce heat. That mix of hot gas then flows into a section of the nozzle, which is called a convergent section. It's getting narrower. That makes the gases move at higher and higher speeds until it gets to the throat of the nozzle, the pinch point of the nozzle, where that flow, if the pressure conditions are right, will hit the speed of sound. Once you go past the speed of sound, if you try to continue making the nozzle narrower, it actually doesn't work. The stuff doesn't continue to expand. So you actually have to expand now. You have to have a divergent portion where the flow continues to accelerate. That's a convergent section. And there the flow is supersonic. As the flow is moving through the nozzle, temperature and pressure are dropping. Because temperature and pressure are dropping, you have to conserve energy. Where is that energy going? It's going into the kinetic energy, the energy of motion of the gases coming out the back. All right. So again, a nozzle is basically converting thermal energy to kinetic energy. That's energy of motion. That gives me an exit velocity. Remember, that exit velocity is what contributes to that momentum coming at the back of the engine that produces my thrust. All right. I want to come back to the point of efficiency. I said rockets can be very efficient, right? Let's take an example. And this is an ideal example. This is a hydrogen-oxygen rocket. So I've got hydrogen for my fuel, oxygen for my oxidizer to burn with the fuel. Let's assume I burn it in what's called a stoichiometric mixture, so that when I'm all done with that reaction, I've burned all of my hydrogen with all my oxygen, which, by the way, turns out not to be the way you would design a hydrogen oxygen rocket. Actually, always tend to make it a little bit hydrogen rich for details we won't go into. But first order, let's start with that. You'll produce 13 million joules of energy for every kilogram of hydrogen of water that you produce from that reaction. So let's do a quick calculation. If all of that energy, all of that thermal energy, becomes the kinetic energy of the water going at the back of the nozzle, then you would get a maximum specific impulse of something on the order of about 520 seconds. Actual specific impulse for some of the best hydrogen oxygen engines we build is in the 450-second range. That's amazing. Rockets are incredibly, incredibly efficient devices, especially chemical rockets. And I want to keep that in mind. I can't think of another type of engine that we've ever built which can approach those levels of efficiency. All right. So with that characterization in mind, let's just talk about the types of chemical rocket engines that are available. And these are chemical. All right. So remember Robert Goddard, 1926, did his liquid fuel rockets. We still fly liquid fuel rockets today. Liquid fuels produce the highest specific impulses of chemical rockets. They have advantages. I've got a liquid fuel rocket. I've got liquids in tanks. I have plumbing systems that somehow get that liquid fuel into a combustion chamber. In some cases, I can throttle that fuel, not in all cases, but in some cases I can throttle that, which means I can adjust the thrust level, or I can turn off the rocket. Maybe I can turn it back on. Liquid fuels often, in some cases, some of the more effective liquid fuels have to be stored as very cold liquids. For example, hydrogen and oxygen are stored as very cold liquids. So that's a challenge. It introduces some handling issues. Some of the liquid chemicals associated with liquid fuels can be dangerous to handle. Things like hydrazine, a chemical that's often used in liquid propellants, is pretty dangerous. Even liquid oxygen, by the way, is very dangerous to handle. We tend to think, hey, oxygen, we breathe it, it's in the atmosphere. Pure liquid hydrogen is one of the most difficult substances to handle known to humankind. If oxygen gets in contact with skin, it can burn. If it gets in contact with any hydrocarbon-based material, it can spontaneously combust. So you have to respect the chemicals that go into liquid fuel rockets. The other thing about liquid fuel rockets, because you've got tanks and plumbing systems and ways of pumping those liquid fuels into a combustion chamber, that tends to add weight. So liquid fuel rockets tend to have higher weight for a given thrust level compared to the solid fuel rockets. And that leads to solid fuel. So solid fuels, by their nature, because of the chemicals that are used for solid fuels, they tend to have lower specific impulses. So less bang for the buck. But they tend to have really high thrust because they're relatively dense. You're expelling lots of mass. And also, you don't need lots of plumbing. You don't need pipes and pumps. A solid fuel engine is generally it's like a Roman candle. You fill a chamber with a solid fuel. You usually pour it as a liquid. It solidifies. You light off that solid fuel rocket, and once you light it, it goes. Solid fuels have lots of advantages. They are storable. You can put a solid fuel missile into a missile silo, put it in the ground for decades, and you don't have to worry about having to refuel it, or obviously you monitor the status of the fuel. But that's a big advantage. They're relatively simple designs. A solid fuel engine is really just a canister, a metal canister that's filled with some solid material. They do have a disadvantage that every once in a while, solid fuel rockets will explode. You can get into combustion instabilities. The rate of combustion of a solid fuel is a function of the exposed area. So if you get a little bit of extra exposed area, maybe a crack in that fuel, you get a local spike in combustion rate. That can increase pressure, which increases combustion rate. And if under certain conditions, that can become a runaway effect and lead to an explosion. Solid fuel rockets also have a problem in most cases. Once you light it, you can't turn it off. Right? There's no valve to shut down. Now, there's another type of rocket, chemical rocket engine, that tries to combine usually a solid fuel with a liquid oxidizer. So, for example, you might do rubber fuel with liquid oxygen, or carbon monoxide, or some other oxidizing material. If you do that right, you try to capture the best of both worlds for liquid fuels and solid fuels. If you do it wrong, you get the worst of both worlds. So hybrids have not seen as much adoption into common use, but for obvious reasons, because you might get the best of both worlds. In fact, if you do it right, you might even do better than both worlds, because hybrid fuels don't have oxidizer embedded in them. So they actually be safer to handle than either solid fuels or liquid fuels. So that's obviously a big advantage. Solid fuels are characterized by the rate at which the fuel recedes. So you want to measure performance of a solid fuel. Usually do it in a chamber where you take a sample of that fuel, you ignite it, and you watch how it burns. That's the regression rate. That regression rate tends to be sensitive to chamber pressure, the pressure inside the rocket. That in turn is a function of regression rate. You burn faster, more fuel is consumed, more heat is released, pressure goes up, fuel burns faster, rinse, lather, and repeat. And that's why under some conditions, a solid fuel rocket actually can have an instability and ultimately explode. Solid fuel grain design is a science and an art in and of itself. Grain is what we call the fuel once it's poured into a solid fuel rocket. Not all solid rockets are lit at the end and then just burn down the length of the rocket. In most cases, for our larger rockets, we actually bore out a hole in the center of the fuel, and we have it burn from the center on out. Now, if you think about that, if I've got a cylinder, and I fill that cylinder with a solid fuel, and I light a hole down the center, as it burns, the radius of that center gets larger. The surface, the circumference of that circle gets larger, so the burn area gets larger. And so there are ways to mitigate that. One is you could do different patterns for the fuel. You could do a star pattern so that the prongs of the star burn. And if you do it right, you can actually control the surface area to a certain point as you burn that fuel. And again, there's an art and a science to that. Okay, so let's go back to performance of a rocket. How do you get the most performance out of a rocket? One is use chemicals that release the most energy. And then you want the lowest molecular weight, because kinetic energy is equal to 1/2 times mass times velocity squared. So there are lots of chemical combinations that release tremendous heat, but the next thing you look for is a practical combination. For practical purposes, hydrogen oxygen is about the most energetic combination. There are other things that will give you a higher specific impulse. For example, lithium, fluorine, and hydrogen burned in combination will give you specific impulses in the 540-second range. That's almost 100 seconds better than hydrogen oxygen. The problem is fluorine is really nasty stuff. So that would be a horrendous handling problem. So you're not going to see any large-scale lithium, fluorine, hydrogen rockets in operation. There are other considerations, though. There are some chemical rockets where you have only a single substance, a monopropellant that you induce to break down, release heat, for example, with some catalyst. Hydrazine is an example that hydrazine actually can be used as either a monopropellant, a single thing, or it can actually be burned with oxidizers. I mentioned one of the advantages of solid fuels is that you want it to be storable. Same thing with some liquid fuels. There are liquid fuels that are more storable than other liquid fuels. A liquid fuel that, for example, doesn't have to be stored as a very, very cold liquid is obviously easier to store than something that I have to keep under constant refrigeration. I might take a performance hit to go with a storable fuel, but that would be something that I would accept because of the overall system design. And then finally, you'd like to go to higher density fuels because you want to get the smallest volume with the smallest tank for a given mass of fuel, because that reduces the weight of the structure of the rocket. That gives you a more advantageous mass fraction for the overall system. All right, one other type of rocket I want to talk about, I alluded to it earlier on, is the nuclear thermal rocket. And I mention this because this is a rocket technology that's been around for decades, but I believe it's making a comeback. It's making a comeback due to efforts of some government agencies and private companies that are investing. The basic principle behind a nuclear thermal rocket already outlined, which is you uncouple the source of the energy from the reaction mass that goes out the back of the nozzle. In this case, the source of the energy is a nuclear reactor. So you've got fission products, fission reactions that are producing heat. I run some working fluid through that reactor. That fluid gets really hot and expands out a nozzle. The best ISP that you can get, best specific impulse, is with the lowest molecular weight. So the fuel of choice in that case is atomic hydrogen. Unfortunately, you can't use atomic hydrogen because we don't know how to store atomic hydrogen. So we go with the next best thing, which is molecular hydrogen, H2, but still much lower molecular weight. So it gives you the highest specific impulse. There was a program in the 1960s that ran until 1973 called NERVA that was going to produce a working nuclear rocket. NERVA demonstrated specific impulses in the 800-second range. They ran the NERVA engines for tens of seconds on the ground. And so that was specific impulse achieved almost 60 years ago, over 50 years ago. That was twice any chemical engine that we can produce today. We think nuclear thermal rockets could do better than that, better than 1,000 seconds. And so you imagine the applications of that. First, if you want to go to Mars, a nuclear thermal rocket is a really good way to do it because it gives you a relatively higher speed trajectory to Mars. But from a military standpoint, that sort of thrust level for a given fuel consumption means you have high acceleration. So if you want to build a rocket vehicle, for example, that can maneuver quickly, that can get out of the way or reposition itself, nuclear thermal rocket could be very, very attractive. And in fact, there's a program at the Strategic Capabilities Office as we speak that's looking at just that technology. Another way to uncouple the energy source from the mass is to use an electric engine. And that basic principle is I use some form of electromagnetism to accelerate a plasma. Right? It could be a charged plate that accelerates a plasma. It could be a magnetic field in some way. Electric rocket engines have also been around for decades. And we know that the specific impulses of these things can be in the thousands of seconds. In fact, within the community of electric propulsion, we often say that the ISPs are too high. And that should make you scratch your head a little bit, except I'll remind you of the argument that I made earlier, that if the engine weight is really large, I have a disadvantageous mass fraction. In other words, the final weight of the whole system is close to the initial weight. And so the overall delta V of the rocket isn't that good. So a lot of the research that's been underway in the electric propulsion field over decades has actually been to reduce the specific impulse of these engines, which means reducing the power requirements. So you reduce the weight of the power system. Up until about 15 years ago or so, electric propulsion was something that had been demonstrated in the laboratory, flown in a few experiments. Now it is accepted technology. There are lots of electric propulsion systems available today. They wind up being very, very effective, especially if you don't care about thrust levels, because they have very low thrust levels. But if you want something where you've got a very small amount of fuel that can run for a long period of time. And indeed, there are even some deep space missions for which electric propulsion is very advantageous, because even though the thrust levels are low, so the accelerations are low, they can be turned on and left on for very long periods of time. So electric propulsion is the tortoise to chemical propulsion or nuclear propulsion's hare. And sometimes slow and steady wins the race. On one note, people will sometimes say electric propulsion systems have higher efficiency than chemical. Nope, that's not true. They actually tend to be lower efficient. A lot of the energy that goes into an electric propulsion system is not useful propulsive energy. It gets lost in other ways. But the ISP is high enough that it becomes very attractive. And I'll also point out the trajectories that are often associated with those low thrust levels tend to require higher delta V. So, for example, if I want to use an electric engine to go from Earth to the moon, the overall delta V will tend to be higher than if I use a chemical engine to do the same mission. And that has to do the quirks of orbital mechanics and the energy that and the delta V that's required to get from point A to point B in a gravitational field. So keep that in mind. Electric engines aren't the solution to all problems. I'll also note that that source of energy that powers an electric propulsion system can come from a variety of sources. It could be a nuclear reactor. It could be solar cells. It could be some other form. It could be batteries. It could be some other form of electric power. And that gives you tremendous flexibility when you're designing an electric propulsion system. All right. Let's close out by talking about some exotic rocket concepts. And this is my favorite part. So what's on the horizon? None of the ideas that I'm going to talk about are really new ideas. They've frankly been on the horizon for decades, but they all have their various attractive aspects. All right. The first one I've got listed there is nuclear fusion. All right. I talked about nuclear fission reactors applied to nuclear thermal rockets. But what if instead of nuclear fission, I could use nuclear fusion? Well, the very first objection you should raise to that is, wait a minute, we've been working on fusion power for how many decades, and we haven't been able to get it to work on the ground. That's true. We have not. But there is an argument to be made that a nuclear fusion rocket would be easier to design and build and make operational than a nuclear fusion reactor. There's a lot of the technology that goes into a nuclear fusion reactor is in controlling the reaction, making it stable, making sure that the reactor doesn't blow apart. With a rocket engine, I've got an entirely open end. I've got stuff flowing out the back. So on a very simple level, you could argue that a nuclear fusion rocket is easier to accomplish than a nuclear reactor. I won't weigh in one way or the other in that debate, but that's something that should be in your head, that's a future potential that's on the horizon. And of course, it's a very, very familiar trope of many science fiction shows. On Star Trek, and they often talk about the impulse engines on the Enterprise. Those aren't the fast and light engines, which are completely impossible as far as we know. Those are the normal engines, but they talk about those as being powered by fusion. If there are any fans of The Expanse out there, they had a fusion-based propulsion system. All right, next, let's do better than nuclear fission or nuclear fusion. What is the best, the way to get the maximum amount of energy out of some particle interaction? Well, it's the use of antimatter. So stepping back, every subatomic particle that we know of appears to have an antimatter counterpart. So for example, normal matter, there's an electron. In antimatter, there's an antimatter counterpart. In normal matter, there's a proton. It's positively charged. In antimatter, there's a negative particle counterpart, an antiproton. And it's also known that when you combine a particle of matter with its corresponding particle of antimatter, they annihilate. So you bring the two together, and the mass ceases to exist and instead becomes pure energy. Albert Einstein told us E equals mc squared. All that mass gets converted into a matter of energy, which is equal to the mass times the square of the speed of light. That is a tremendous, tremendous amount of energy. So let's think about that. If I could use that for propulsion, how cool would that be, or how hot would that be? Now, having said that, there are a lot of practical problems associated with an antimatter engine. The first is we don't have antimatter. The big particle accelerators produce antimatter. We don't have any facilities that focus only on the production of antimatter. The fans of antimatter propulsion would tell you, well, we've actually never tried to produce antimatter in large quantities. And if we had a dedicated facility, we could probably do a better job. But for now, we don't have it. Second problem, how do you store it? How do you store a substance which wants to annihilate when it comes in contact with regular matter? We think there's a solution to that, an electromagnetic trap called a Penning trap. It was conceived of by someone named Penning, and it's been demonstrated that you can store any matter in a Penning trap for a reasonable period of time. How long can you store it in a trap? We don't know yet. There's another challenge. What do you do with all that energy once you release it? Now, remember, in the case of the nuclear thermal rocket, in the case of the fusion rocket, you're using that energy to heat up a working fluid and spit it out the back. So imagine an antimatter engine. You're releasing all this energy and you're trying to heat up a working fluid, maybe hydrogen, really good working fluid, right? Low molecular weight. How do you get the energy from the antimatter into the hydrogen? Well, the problem is antimatter reactions produce energy with very, very energetic subatomic particles that then become gamma radiation. It's very hard to convert gamma radiation into heat energy. So that design of the engine becomes really complicated. We know that there are certain really dense atoms, like tungsten, for example, that will capture gamma radiation and then get hot. So you might imagine a rocket engine that's got lots and lots and lots of tungsten. And you got antimatter that's reacting and it's heating up that tungsten, and then you circulate hydrogen through the tungsten, make it really hot, expand it out of nozzle. The problem is I now have removed, say, all the uranium fissionable material from my reactor, but instead I have lots of tungsten. So I have a really heavy rocket engine, not a particularly good design. So the bottom line is antimatter sounds really good in principle. We just don't know how to build that thing, and we don't know how we would use it. I'm going to touch very briefly on some other concepts, then we'll go to questions and answers. Solar thermal. What if I could come up with a way of removing the fuel entirely from my rocket? And I know of at least one way to do that, and that is something called a solar sail. And I've got that pictured on this view graph. What that basically is a big piece of reflective material. Light of some sort hits that material. When light strikes a surface, it imparts momentum. That could be counterintuitive to us, right? Light imparting momentum, light is applying pressure, but yes, indeed, light applies pressure. The room that you're sitting in right now, the lights that are on from the light bulbs in that room are applying pressure to every surface of that room, to your body. The magnitude of that pressure is infinitesimally small. But if you're in space where there are no other pressures, that effect can be noticeable. So imagine I erect a giant piece of reflective material. Sunlight hits it, imparts a pressure to that material. That pressure, in turn, integrated over the area of that light cell, gives me thrust. Think about it. I just got thrust without having to carry any fuel on board, as long as I have a source of light. It's a great way to get around the solar system. Now, again, the problem is going to be the thrust levels will be really, really small. And a lot of challenges in designing that light cell, so the mass is very, very small. Thrust is equal to mass times acceleration. So if I want to accelerate, I need a low mass. So you got to engineer a very, very thin, highly efficient structure. But if you can do that, you can dart around the solar system for free. Hard to get out of the solar system, though, because the further you get from the sun, the less light you have. Eventually, you get too far from the sun, not enough light pressure. And I might be able to solve that problem if I've got a really powerful laser. That's not the only thing I can do with a laser. I want to come back to the nuclear reactor idea. Instead of a nuclear reactor, we're going to switch gears back. Instead of a nuclear reactor, what if, instead of fissioning material, I had a laser that pointed at a reaction chamber, heated up my working fluid? That'd be another way to design a rocket without fissionable material. I might apply the same principle. Instead of using a laser, capture sunlight, have big mirrors that focus sunlight into a heating chamber that heats some working fluid, expels out the back. So then I get a solar thermal rocket. So the bottom line is lots and lots of interesting ways that I might get away from traditional chemical propulsion, traditional electric propulsion, and even traditional nuclear thermal propulsion. And each of these, frankly, could have applications to deep space operations, even ultimately applications to military operations. So with that, let me close out my formal comments, and I am looking forward to your questions and comments. And normally when we do these, I, as the ETI director, moderate the questions for whoever the speaker is. Since I'm serving both roles today, I will exercise the privilege of both moderating and answering. All right. So first question coming, what are the biggest challenges with rocket engine design? So a lot of the devil's in the detail. So for example, consider a chemical engine. I need to design something where first I get very efficient combustion in a very small volume, to keep the weight small. So I need to have an injector system that injects the fuel, mixes it efficiently, gets it to burn efficiently. I need to design a nozzle that can handle those hot gases. So I often have to actively cool that nozzle. So the thermal management of that whole system becomes really important. Pumping the fuel into the combustion chamber. I need very efficient pumps. In the development of the space shuttle main engine system, for example, one of the biggest challenges was developing the pumps that could get the liquid fuel into the combustion chamber. And then finally, designing an engine that not only works once, but works multiple times, is reusable, is throttleable, is really, really challenging. One of the great contributions we've seen in recent rocket engine developments, for example, those from SpaceX, has been the development of reusable rocket engines that get the cost down if I can refurbish and reuse instead of using my rocket engine and throwing it away. Okay, next question. What would have to happen for rocket technology to be out of date? Ooh. Well, so how do we get away from rocket propulsion entirely? There are a couple ways you might do that. I'll give you my favorite scheme, and it's a science fiction scheme. But if instead of rocket propulsion, I could build something called a space elevator. All right, what's a space elevator? You do the following. Start in geosynchronous orbit around the Earth. Geosynchronous orbit is a special orbit such that whatever is in geosynchronous orbit is situated over the exact same spot of the Earth 24/7. And from geosynchronous orbit, we start building a structure down towards the Earth. We'd have to counterbalance with weight moving out so that the center of mass remains in geosynchronous orbit. If I make that structure large enough, I can eventually get it to reach all the way to the surface of the Earth. Now I have a structure that goes from the surface of our planet all the way up to space. And suddenly I no longer need a rocket. I just need an elevator. All right. I just hop on an elevator that's on that structure and it gets me all the way out to space. Okay. Sounds great in principle. In practice, building that thing is almost impossible. First, only the center of mass is in orbit. That means that that entire structure is under tension. We have no known materials from which to build a space elevator. Even if you look at the best materials we could theorize on about, they're not strong enough to build that space elevator. That's problem number one. Problem number two is you've got this enormous structure, which is penetrating the atmosphere, subject to all sorts of issues, weather problems, for example. Their navigation has, as I said. So bottom line, it is a science fiction concept, but one which we really have no way to do it. But if you can do it, bam, you've gotten rid of rockets. And we got or at least rockets to get to space. We've got a much better solution. Let's see, next question. Since this session is on rockets, can I explain why the Starship exploded? No, I can't. It just happened. I'm sure there's gonna be a team of folks that will be investigating that. But let me leave you with a thought. There is a tremendous amount of energy associated with a launch vehicle. If you, for example, calculate the amount of power, that's energy per unit time, so the amount of power that was being released by the space shuttle when it was taking off from its launch pad, it was equal to about 55 gigawatts. That's the equivalent of several nuclear power plants working in parallel. That's enough power to power multiple mid-sized US cities. When the space shuttle was taking off from its launch pad, when the Saturn V is taking off from its launch pad, when the Starship is taking off from its launch pad, it is one of the most energetic non-nuclear systems we have ever built. That is a tremendous amount of energy. So it's not surprising things go wrong. I mean, think about all the controlled release of that amount of energy. It is a miracle of modern technology. It is a tribute to engineering that it all works and that it doesn't explode every time. I'm going to wax a bit poetic for a moment. There are some people who think that the single greatest artifact that was ever produced by humanity was the Saturn V moon rocket, the rocket that got us to the moon. I'm one of those people. I think it's an amazing system. 365 feet tall, 7.5 million pounds of thrust at takeoff. Remember that the Saturn V took off as this giant rocket stack, and the only thing that came back that landed with the astronauts was a 13-foot diameter capsule, the Apollo capsule. Rockets are systems that almost don't work. It's amazing that they're able to function. It's amazing that we're in an era where rocket propulsion is almost commonplace. And that's a tribute to, I think that's a tribute to us as a species. I'm sorry, I get a little, I wax a bit poetic about rockets, as you can tell. Let's see, next question. Oh, I have a question from a former student. Okay, hello, Nicole. Is current use of electric rocket engines strictly for space, or are there Earth applications? So the simple answer is electric propulsion produces such very low thrust levels. I'm hard-pressed to think of any really practical examples of where I might use an electric propulsion system. Now, never say never. So you could maybe imagine some if you're more imaginative than I am. But the reality is you're only using an electric engine in an environment where you're not dominated by other forces because of those low thrust levels. Here's one. If nuclear thermal rockets have such high ISP, why don't we see them being adopted more? I think it's more culture than science, right? There is a stigma associated with nuclear power, and that ultimately hurt the nuclear rockets. Now, let's make no mistake here. A nuclear thermal rocket engine is spitting out working fluid that is probably radioactive. So you would never use it on the ground. You would never use it to take off. You would only use it in deep space. When you use it, if you've got human beings on the rocket vehicle, you'd have to go through, you'd have to make efforts to make sure that they're not exposed to the radiation from the engine. But does that mean you can't launch a nuclear thermal rocket? No, not at all. We in fact, there is a very strong argument to be made that a nuclear reactor is safer to launch than some of the nuclear thermal generators that we launch on a regular basis with our deep space probes. And in fact, not too long ago, the White House developed, did a formal executive policy on nuclear power in space that specifically called out nuclear fission as being a technology that has to be enabled by simplifying, or at least clarifying, the launch regimen. But I'm actually convinced that it is such an obvious technology. If we're serious about deep space, I'm convinced it's something that we will see in years to come. Will you be able to rewatch the presentation? Yes. All right. Do I see pulse detonation engines as a credible future motor design? Simple answer, yes. So in pulse detonation, instead of having continuous combustion, you do little explosions. Turns out that's a more efficient way to burn fuel. So I think it's extremely promising. They've got challenges. It's not a new idea. It's an idea that we worked on for many years. But if you can do it, you get even more energy out of your fuel than you do with continuous combustion. All right. What is the fundamental equation usage? I think that's referring to the rocket equation, and what the rocket equation basically, it's the guiding principle when you're designing a rocket. All right. If I have a certain change in velocity required for a mission, a certain delta V. For example, if I want to go to Mars, I calculate how much velocity change I need to get there. Then that tells me the required specific impulse, the required engine performance as a function of the weight fraction of my rocket. All right. Alex asks, there was talk a few years ago about inside-out nozzles, plug nozzles. Here's how those work. So instead of having a bell or a nozzle that looks like a bell, I turn the whole thing inside out and I make it a spike. Why is that an advantage? Remember when I derived the thrust equation, I mentioned there's this pressure term that we usually neglect. It turns out the ideal design of a rocket nozzle is such that the pressure at the exit of the nozzle is equal to the ambient pressure around the nozzle. That's hard to do because typical rocket, especially for a launch vehicle, is flying through a range of pressures. I start on at sea level, I start on the ground, I fly up into space where there's really no atmospheric pressure at all. So I'm flying through a range of pressures, and typically I design a nozzle for one specific external pressure, one ambient pressure, and there are all the times I'm off design. If I can turn that nozzle inside out so it looks like a spike, think of it as a giant dental pick, then I exhaust the flow and it's always matched to ambient pressure. Again, old idea, it's been around for a while. My favorite example of that is if you rent a copy of Stanley Kubrick's 2001: A Space Odyssey, he shows in the early scenes of that movie a space shuttle flying up to a space station, and it has an inside-out nozzle, has an aerospace nozzle. So that was from 1968, well ahead of its time. All right, let's see. I've got time for maybe one or two more questions. So here's one about space elevators. Wouldn't building a space elevator require the requirement removal of most all satellites orbiting below the terminus of the elevator? Yes, you'd have to be really, that's exactly right. You'd have to be really careful because you've got this fixed structure and you'd have satellites whizzing by and you'd have to worry about space debris and you calculate the collision cross-section of a space elevator. So yeah, add that to the list of really, really, really big challenges that you're faced with designing a space elevator. All right, I'm gonna answer one more question, which I love, which is has rocket technology plateaued? Very simply, no, I don't think it has. I think there are a lot of avenues. So I mentioned that rocket engines are still about the most efficient machines that I can conceive of. However, there are lots of improvements we can make. Companies like SpaceX are showing us that, right? Having reusable rockets. We see companies now, a company like Ursa Major is using additive manufacturing principles to make rockets that are at much lower cost. So no, I think there's a lot of room to improve rocket engines. I would almost say that rocket technology today is kind of where we were in the 1960s with jet engines. And you look at how good we are at designing jet engines today, how well we understand all the parts of that engine, how efficient we can build those devices, how good we are at refurbishment, replacement. I think that's the direction we need to go for rocket engines. And that's the direction that the industry is pushing us. And seeing all these tech companies that are in this realm, companies that are pushing nuclear thermal propulsion, for example, companies that are pushing additive manufacturing. I think it's a really exciting time for future developments of rocket engines. All right, with that, let me close out the webinar part of this. Let me thank all of you for your attendance, for your participation. I hope you found that of value. We will post the recording online just as soon as is possible. I would ask, complete the survey that pops up on your screen, the conclusion of the webinar. If you love this webinar, we would like to hear from you. If you hated this webinar, we would also like to hear from you, but in that case, my name is Dr. Arun Seraphin. That's a little inside joke. If you have any other feedback about this series, if there are topics you want us to cover, please email us at eti@ndia.org. Also want to take this opportunity to highlight some upcoming ETI events. You'll see that on our website, and most especially, we have a big conference planned for the Emerging Technologies Institute at the end of August, August 28th through 30th, down at the JW Marriott in downtown Washington, D.C. It will be the Emerging Technologies for Defense conference event of the decade, certainly of the year, and I urge you all to check out our website and attend. And here you'll see on your screen are the list of other upcoming events, including a hypersonic supply chain report we'll be releasing on May 11th. We'll be doing a 101, one of these webinar series on printed circuit boards in June. And then most immediately, introduction to defense technology, to Defense Technical Information Center, DTIC, on May 3rd, and an Agile Software Development 101 on May 10th, also at 1 p.m. Eastern Time. With that, thank you once again for your attention. Thank you for your participation, and I hope you all have a wonderful rest of the day.